Okay, so this relationship between the force and the change in momentum, that is that the force equals the change in momentum over time, can be very useful because can be very useful when you're studying collisions of any kind, because this is always true for collisions of any type. And so that makes a very useful tool in order to determine what are the forces involved in collisions. Because, as I said, it's very difficult to measure a change or a force that acts on an object. It's just intrinsically difficult to measure forces without specialized sensors. But it's very easy to measure an object's change in velocity and to measure a duration of time. So we're going to watch a collision video. You can pick up in this video if you want. I think it's really interesting, so you can watch the whole thing. But if you want to pick up at about 3 minutes or so, this talks about how they study pedestrian collisions. That is when cars strike pedestrians. And I just want to get a rough estimate of the force that impacts this person when this car strikes the person at a certain speed. So you can watch the video now. You can do that by clicking here. Now, in the video, we have a car. It's a Honda. All right. And it's traveling at 40 kilometers per hour. That's approximately 10 meters per second. All right, so it's traveling at about 10 meters per second, and it strikes a person. Now, if you watch closely, right around 320 or so, you can see that the car is in contact with the person, for about a meter or so. So it's pushing on the person, and you can see some marks on the ground that mark out meters. So it's in contact with the person for about a meter, and in a meter, so it's in contact for about x equal 1 meter. This is its velocity. And so if I want to find the time that it's in contact with the person, that time is going to be x over v, or 1 over 10, 1 meter over 10 meters per second. And that'll give me some rough estimate of the time. So this person is struck by the car and remains in contact with the car for about 1/10 of a second. All right, so then we can say then that the force is imparted on the person over about 1/10 of a second. Now, obviously, that's not entirely true. We're just sort of getting a rough estimate of the force, because when the car first strikes the person, it's going to have a larger force, and then that force will decrease. But this will give us sort of a good first rough estimate of the forces involved. So that's the time. And then you also see that the person who has an initial velocity equal to 0 meters per second has a final velocity that's approximately equal to that of the car. So its final velocity goes up to about 10 meters per second. So that's going to give us our delta V. This will give us our delta T. And then we can find the mass of the person, or we can estimate the mass of the person. Let's say this is a big person, just to make the numbers easy. And we'll say it's about 100 kilograms. Likely more around 70 kilograms. But just to make the numbers easy, let's say 100 kilograms. All right, so then if I want to find my force is just delta P over delta T. That's going to be the mass times my change in velocity over my change in time. That's 100 kilograms. My change in velocity is going to be 10 minus 0 meters per second, divided by my change in time, which is 0.1. So that gives me my my force, which is going to be 1,000 over 0.1, or 10,000 newtons. That's a pretty darn big force. I mean, and also you need to remember that this person was struck right about here. All that force is basically on one position, on their hip or so. So that's a large force, 10,000 newtons, which is about a quarter pound, so a few hundred pounds of force, all right there on the hip. I think this is actually a fairly conservative estimate for that force.